Okay, so today we're going to derive kinematics and kinetic equation for linear and rotational. Now, there are three equations that you should know that will help us derive kinetics and kinematics equation. And those three are the big dogs of classical mechanics and further application down the line. So, you must know that velocity is equal ds over dt, which is change in displacement over change of time. That's number one. Number two, you need to know acceleration, which is dv over dt, which is change in velocity over change in time. And there's another form for acceleration, which is dv ds times ds dt, which then would be v dv ds. How did I know this is v? Well, it came from here. And since this is equal to this, so that's why this is v. So this turns into v right here. Alright, so that's for acceleration. And for, now this set right here is for deriving kinematics equation. And finally, to derive our kinetic equation, F equals ma. So that's all you need to know. You need to know this equation, and this equation right here, and you're set. And now we're going to derive our kinetics and kinematics equation. Okay. So first, let's start with v ds dt. Okay. Let's cross product that. So v dt equals ds. Now take the integral, assuming the time starts at initial to t final, s initial, s final. Then it would be v delta t is equal to delta s. Okay. Let's hold on to this. Now, on to the next equation. A is equal to dv dt. You did the same thing over here. Take the initial, take the final, take the initial, take the final. And that would be A delta t is equal to delta v. Okay? Now, delta v, what it is v final minus v initial. We all know that. So then, it would be like this. And that's our first kinematic equation right here. Okay. Since now assume that this v right here is v final. Okay? So then this equation would be v final delta t. All right? Okay. Delta. Yep. And this is our second equation. Our third equation would use A dv ds multiplied by v, which then would be a delta S is equal to delta V squared over 2. How do we get that? Because S dV here S V squared over 2. That's how we got that. That's how we got this to this right here. So then just move this further down. Then we'd get 2a delta S is equal to Vf squared minus initial squared, which then would be Vf squared equals to 2a delta S plus V initial squared. And that's it. Here's our 3 kinematics equation. All right. So let's move on to kinetic equations. Okay. So for kinetic equation, we start off with F is equal to ma. Now, if you remember, A is equal to dV dt or v dv ds. So we're going to use these 2 forms of acceleration to get 2 forms of kinetic energy. Well, these 2 forms can get us also like another alternative for that. So by the end of this, we'd get work is equal kinetic energy. We got impulse is equal to momentum. So let's start. F is equal to ma dv dt, which then is equal to F dt equals m dv, which would equal to F delta t equals m delta v. This right here is an impulse. This right here is a momentum. Okay, that's our first equation of kinetic energy. On to the next. F is equal to m v dv ds, which then would equal F ds is equal to m delta v squared over 2. This would be F delta s right here, which then this would be work. This would be kinetic energy. And that's our equation for number 2. Therefore, work is equal to F ds, impulse is equal to F dt, and momentum, I spelled that wrong, m dv. Alright, now we got momentum, impulse, kinetic, work. There's only one thing that's missing, and that's potential energy. So for potential energy, super easy. We still use F is equal to ma. Now we assume that A is G. Okay, so the gravitational force since potential is just dependent on the height of something to the surface. Okay? And its weight and gravity. Okay. So, therefore, F is equal to mg. Okay. And work is equal to F delta S, which then, assuming delta S is the displacement of the height, so therefore it would be F delta H, which would be mg delta H, which this would be called potential energy. Energy. So, let's organize our information. Work, F delta S, impulse, F delta T, kinetic, M delta V squared over 2, potential equals mg delta H, and momentum, which is the hardest thing for me to write. I need to practice on that. But yeah, that's all there is for kinetic. And also for kinematics equation. Now these equations also the only restriction with these is if the acceleration is constant. Okay? So in some cases you can't always rely on kinematics equation. All right. Now these equations are for linear equations. Now let's talk about rotational. In rotational world, S is equal to theta. We got that. T is equal to T. Time is equal to time. Nothing is changing about that. V, which is the linear velocity, is equal to the angular velocity, which is squiggly W right here. Then we got A, which is the linear acceleration, is equal to the angular acceleration. And M, which is mass, is equal to inertia. And F, which is force, is equal to torque. So this is the rotational world. So when V equals to ds dt, in the rotational world, we said V is equal to the angular velocity, and ds is equal to d theta, and that's dt. Same go for the acceleration. A is equal to dv dt, which it would be dw over dt, or, hold on, you know what, I'm going to write this down, ds, which would be the angular d theta. And how we got that? We got this because it's this right here. Okay. And F, you guessed it, F equals ma, which it would be torque, inertia, acceleration. All right. Oh, sorry. Breathe. Yep. Yep. Right here. Okay. And same thing with our kinematics equation. I'm gonna copy paste them, honestly. I'm kind of lazy. Copy, paste. Okay. So this would be delta theta equals to delta t plus delta t. This would be like this. This would be like that. Okay. Same goes for our linear in here. Copy, paste, equal to t delta theta, t delta t, inertia, oh, sorry. Yep. And that's it.